This is Mrs. Zappia with Lesson 11, Definition of Congruence and some Basic Properties. Student outcomes for this lesson. Students know the definition of congruence and related notation. Students know that to prove two figures are congruent, there must be a sequence of rigid motions that maps one figure onto the other. Students know that the basic properties of congruence are similar to the properties for all three rigid motions: translations, rotations, and reflections. Our essential question for Lesson 11. Which rigid motion is used to bring together at least one pair of corresponding points, which are vertices? Sequencing basic rigid motions has been practiced throughout the lessons of Topic B in this module because in general the sequence of basic rigid motions is called a congruence. A geometric figure S is said to be congruent to another geometric figure S' if there is a sequence of rigid motions that maps S to S'. The notation related to congruence is a symbol. The symbol for congruence is an equal sign with a wave above it. When two figures are congruent, like S and S', we can write S is congruent to S'. S is congruent to S'. We want to describe the sequence of rigid motions that demonstrates the two triangles shown below are congruent. That is, triangle ABC is congruent to triangle A', B', C'. What rigid motion will bring the two triangles together? That is, which motion would bring together at least one pair of corresponding points? Taking our piece of tracing paper and placing it on triangle ABC. The first thing that you want to do is to translate one point to its corresponding point on the second figure. I have chosen to translate point A to A'. You could also do B to B' or C to C'. So I'm going to map it along the vector, and then once I have A on A', then I can rotate my figure and it maps triangle ABC onto A', B', C'. So our sequence that we did, the first thing that we did was to translate point A onto A' by using a vector A'. The second thing that we did was to rotate around point A' d degrees. After these two rigid motions, we have shown that triangle ABC is congruent to triangle A', B', C' through a sequence of a translation followed by a rotation. Notice that only two rigid motions were needed for this sequence. A sequence to demonstrate congruence can be made up of any combination of the basic rigid motions using all three or even just one. The concept of congruence between two geometric figures is one of the cornerstones of geometry. Congruence is now realized as a sequence of basic rigid motions that maps one figure onto another. Please add that to your notes. In example 2, it said that S is congruent to S' if there's a congruence so that the congruence of S is equal to S'. This leaves open the possibility that, although S is congruent to S', the figure S' may not be congruent to S. So what we want to know is if S is congruent to S', is S' congruent to S? And that's what example 2 will show us. We take our figure and translate it along vector MN, and then reflect it across line L. And that maps S onto S'. So that shows that those two figures are congruent. The question is asking, is S' congruent to S? If we can map it back onto S, then it is congruent. To map it back onto S, remember to undo a reflection, you reflect again. So we will reflect it over line L, and then instead of translating along vector MN, we will need to translate along vector NM, such as this. So this is M and this is N, so this vector is called NM. Then we'll translate along that vector, and it maps S prime back onto S. So the question was asking, if S is congruent to S prime, is S prime congruent to S? And our answer is yes, it is. We have shown this by doing a translation along vector MN, followed by a reflection across line L. Then to map it back onto S, we did a reflection across line L, followed by a translation along vector NM. And notice the way that that's written, the order and the arrow. In our next exercise, describe the sequence of basic rigid motions that shows that figure S1 is congruent to figure S2. The first thing I want to do is translate one point to another. Let's call this point A and this point B. In order to translate point A to point B, I need a vector. So go ahead and draw vector AB.
Once you have your AB vector drawn, place your tracing paper over the figure. Translate it along vector AB. Then rotate on point A until the figure is lined up with the long side of figure 1 with figure 2. Once it's lined up, then you'll reflect over the longest side. Reflect, and you have figure 1 mapped on to figure 2. What we did is we translated along vector AB, then rotate around point B, D degrees. Finally, reflect across the longest side of the figure. This shows that S1 is congruent to S2 because S1 can be mapped onto S2.
In exercise B, describe the sequence of basic rigid motions that shows that figure 2 is congruent to figure 3. So we want to map figure 2 onto figure 3. We're going to translate along vector BC. Go ahead and label your points A, B, and C. In order to translate along the vector, you need to draw the vector from B to C. You'll also want to extend your line so that you can move it in a straight line. Alright, so I have traced my figure and I have my arrow on the vector. I'm going to translate it along the vector, and then I'm going to rotate it around point C, and that maps figure 2 onto figure 3. We translate it along vector BC. We rotate around point C D2 degrees. And notice that I've labeled the number of degrees D2. Up here, this was D1 rotation, and this is D2 rotation. So this maps S2 onto S3, and it shows congruence. Figure S2 is congruent to figure S3. or C. Describe a sequence of basic rigid motions that shows that figure S1 is congruent to S3. I've traced my figure, and so I'm going to need to move it over here. So the first thing I need to do is I need to have a vector going from A to C. Then move the starting point A to the ending point C. Once you have it on point C, then you can rotate your figure. Notice that I will also need a reflection. I'm going to have to reflect it over the longest side. We had to translate along vector AC. We rotated C d3 degrees, and then we reflected across the longest segment. And this showed that figure S1 is congruent to figure S3. If figure S1 is congruent to figure S2 and figure S2 is congruent to S3, did we really need to do all that work in part C to show that figure S1 is congruent to S3? Well, we did not necessarily need to do all of that. We know that translations, rotations, and reflections preserve angle measurements and lengths of segments. For that reason, we know that if S1 is congruent to S2 from part A, and S2 is congruent to S3 from part B, then we can say that S1 is congruent to S3, which we proved in part C. So we have some properties of congruence. The first property of congruence. A congruence maps a line to a line, a ray to a ray, a segment to a segment, and an angle to an angle. Now these look very similar to the properties of basic rigid motions, and these are the properties of congruence. The second property of congruence is a congruence preserves lengths of segments. So if you know two figures are congruent, then their corresponding segments are congruent. And congruence 3. A congruence preserves measures of angles. And that means if two figures are congruent, their corresponding angles are also congruent. Exercise 3. Perform the sequence of translation followed by a rotation of figure XYZ, where T is a translation along vector AB and R is a rotation of D degrees. You choose D, around letter O. Label the transformed figure X prime, Y prime, Z prime. Will XYZ be congruent to X prime, Y prime, Z prime? Hopefully you can answer that question without actually having to do the sequence of rigid motions. But in case you're not convinced, here's our figure. So first we're going to translate along vector AB and then rotate along point O. And you can choose your degrees. So I'm just going to go that far. And then here is my new figure. And labeling your figures before you rotate them can help you to label them once they are completed. So I'll darken that here. And this was point Y, X, and Z. And then to prove that they are congruent, you can measure. So XY is 2 centimeters, XY is 2 centimeters, XZ is 2 centimeters, XZ is 2 centimeters, and ZY 17. Alright, so 17 centimeters, or millimeters rather. So the answer is yes. And we've proven that. We know that the segment lengths will be preserved, the angle measures will be preserved. In this lesson, we have learned we have a definition of congruence, a sequence of basic rigid motions. The properties that apply to the individual basic rigid motions also apply to congruences, and we now have a new notation for congruence, which is an equal sign with a wave above it.